Hello, everybody. Thanks so much for joining me today. My name is Michael. Hope you're having a wonderful day so far. Today marks the start of the Harvard CS50x course, their revamped version for 2025. This is a condensed version of the live stream I did and hosted a live watch-along of the Week 0 lecture. If you're interested in following along live on the streams, please consider joining me during the live streams as I watch these lectures.
So it's now time to solve with actual code some actual problems, albeit in a fun and visual and audio way. But recall that where we left off was this. Like starting next week, you'll be writing code that ultimately looks like this. But thankfully, you will not be writing zeros and ones. And no normal person, myself included, can understand what all of these zeros and ones are at a glance. We could take out some paper pencil and probably figure it out very tediously. But this is exactly the point. Computers only understand this stuff. But what we as programmers will start writing today and beyond is code at a higher level. And indeed, this is going to be frequent within computer science, where there's different levels of abstraction that we operate at. And the lowest level, the nittiest gritty, is like the zeros and ones that computer understand. That's it in this class for zeros and ones. Hopefully, you at least have wrapped your mind around why zeros and ones can be used in triples and as bytes to represent higher and higher numbers. But let's just now agree that computers can do that. Let's abstract away from that detail and focus on higher level languages than zeros and ones, namely a language like this. So this is an example of the very first programming language I learned back in the day, as per that homework, in a language called C. It's an older language, but it remains one of the most popular languages and omnipresent languages nowadays because it's incredibly fast and it's particularly good at making devices operate quickly. For us pedagogically, the value of C is not that you're probably in Silicon Valley and other such jobs going to be using C yourself that much, but because it's going to provide a conceptual foundation on top of which we introduce other languages like Python, which is newer and improved, so to speak, that gives you more and more functionality sort of for free out of the box by abstracting away some of the stuff we'll focus on in the coming days first. So at the end of the day, you should better understand languages like Python and JavaScript and SQL because of your underlying understanding of a language like C.
Exactly. That's why we're doing this course.
But this is too much for the first day. Many of you will think that this is too much for the second week. But in fact, C is really only sort of scary looking because all of this darn punctuation and syntax, the semicolon, the parentheses, the double quotes, the curly braces, and the like. And I concur. This is intellectually uninteresting. And a lot of the challenges early on when learning programming is you just don't have the muscle memory like that I or some of the teaching fellows might for knowing what symbols should be where. But that's going to come with time and practice. I guarantee it. What we'll do for today, though, is just throw away all of that intellectually uninteresting detail and focus really on ideas. And some of you might be in your comfort zone here, because if back in middle school you were playing with a programming language called Scratch, you were probably using it at that time just to have fun in class or out of class, making games, animations, interactive art. What you probably didn't use it for, at least in middle school, was to consider and explore programming languages themselves. But what's wonderful about Scratch, which is this graphical programming language from down the street at MIT, where it was invented some years ago, is you can program not by using your keyboard per se, but by dragging and dropping puzzle pieces, otherwise known as blocks, that will snap together if it makes logical sense to do so. And what you won't have to deal with is parentheses and double quotes and semicolons and all of that, at least until next week. But the nice thing about Scratch is that after this week and after the so-called problem set 0, the first assignment in which you'll use Scratch, you'll have a mental model via which it will be easier to pick up all of the subsequent syntax as well. So let's see how we can start programming in Scratch by making the simplest of programs first. You can do this at scratch.mit.edu. You needn't do this now in the moment. Problem set 0 will walk you through all of these steps. But what I've done here is opened up at scratch.mit.edu, precisely the default web page therein. This is after having clicked the Create button in Scratch, which is going to allow me to create my first program. But first, a tour of the user interface here and what is ultimately available to you. Well, within the Scratch environment, we'll see a few different regions of the screen. One, we have this palette of puzzle pieces at left. The blue ones relate to motion. The purple ones relate to looks. The pink ones relate to sound and so forth. So the color of the blocks just roughly categorizes what that block's purpose in life is. We're going to be able to use those puzzle pieces by dragging and dropping them from left to right. In the right here, in the middle of the screen, is where I'm going to write my actual programs. This is where I'll drag and drop these puzzle pieces, lock them together, and actually write my code. What am I going to be coding? Well, I'm going to be controlling one or more sprites. Much like in the world of games, if familiar, a sprite is like a character that you might see on the screen. The default character in the world of Scratch is, in fact, a cat that looks like this. And if, in this case, I have just one cat, I can then make that cat do things in his own little world at top right by making the cat move up, down, left, right, spinning around, or doing other things as well. But if you want to introduce a dog or a bird or any number of other custom characters, you just add more sprites, and they get their own place in that same world. As for how to think about movement in this world, it's actually pretty familiar, even though it gets a little numeric for a moment. If Scratch at the moment is in the middle of the screen, the cat is at 0, 0. If you think about x, y coordinates or latitude, longitude, if you move the cat all the way up, this would still be x equals 0, but it would be y 180. What's the 180? 180 pixels vertically, or dots on the screen. This is negative 180 pixels on the screen at the bottom. By contrast, if you go left and right, your x value might change, negative 240, but y is 0, or positive 240, and y is 0 as well. But most of the time, you won't need to know or care about what the pixel coordinates of the cat are. All you're generally going to care about as the programmer, most likely, is do you want the cat to go relatively up, down, left, or right, and let MIT figure out the mathematics of moving this thing around in most cases. All right. So let's go ahead and introduce the first of these programs by doing something quite simple, as we did in C there, but a little more simply by writing code as follows. I'm going to go back to scratch.mit.edu. I've already clicked, per before, the Create button. And if I click on the yellow category of blocks here at left, and I'll zoom in, we'll see a whole bunch of yellow puzzle pieces. And probably the most common one you will use to write code in Scratch for just this first week is literally when green flag clicked. Why? Well, if we go back over to the cat's world at top right, notice that above the cat's rectangular world, there's not only a green flag for starting, there's a red stop sign for stopping as well. So let's do this. Let me go ahead and click and drag when green flag clicked anywhere into the middle and let go. And now I'm going to go to Looks, and it looks like there's a whole bunch of purple puzzle pieces here. I'm going to choose something simple like Say Hello, drag it, and notice if I get just close enough, it's going to want to magnetically snap together. So I'll just do that, and it does its thing. The fact that there's this white oval with text means that is an input to this Say puzzle piece. I can literally then change what the input is if I want to more conventionally say hello, comma, world, which in fact, according to lore, was the very first program written in C, and nowadays in most every language, including in Brian Kernighan's book. So hello world is generally the first program that most any programmer first writes. So that's it as programs go. Let me go ahead and zoom out here. Let me go over to the right and click the green flag, and somewhat excitingly, maybe underwhelmingly, we've now written a program that quite simply says hello world on the screen. Now let's make this a little more technical for just a moment. What is this here puzzle piece, as I keep calling it? It's actually a similar, it's an incarnation of one of the ideas from our pseudocode before. What did we call those actions and verbs last time in my pseudocode? Functions, that's right. So these purple puzzle pieces here are indeed functions, and some functions, as we can see, take inputs like hello, comma, world. After all, how does Scratch know what to say? You have to provide the cat with input, which is to say functions can indeed take inputs like this. In this case, one input, but we'll see opportunities for passing in more input as well. What the cat is doing, though, visually on the screen here at top right, is what's generally called a side effect. Sometimes when you call a function, it does something visually. And in this case, you're seeing literally a cartoon speech bubble, hello world. That is the side effect of this function. So if we now want to map this to our world of inputs and outputs and see where this side effect is, this is the paradigm I proposed at the start of class that is computer science in a nutshell, and will be the framework we use literally throughout the class, no matter how the languages in particular evolve. So what's the input to this particular program? Well, this white oval, hello world, is my input. The algorithm, step-by-step instructions for solving some problem, is implemented in code, this language called Scratch, by way of this purple puzzle piece. And the output of that function given this input is the side effect whereby the cat indeed says hello world visually on the screen in that speech bubble. So the exact same paradigm with which we began today governs how exactly this cat here works. Well, let's actually go back to this program and make it a little more interesting than that. Let me go ahead and click the red stop sign. And let me actually use a different type of puzzle piece, another function that does something a little different. First, I'm going to get rid of the say block. So I'm going to not only pull it away, I'm going to drag it over anywhere it left and just let go, and it will delete itself automatically. Okay. Or I could right-click or control-click, and from a little menu, I could also explicitly say delete. And what I'm going to do now is under sensing, which is a light blue shade of puzzle piece. There's a whole bunch here, but I'm going to focus on this one. Ask something and wait. And the default text is what's your name, and that's fine. But because it's a white oval, that input can be manually changed by me if I wanted to change the question. I'm going to drag it over here. It's going to magnetically snap together. And I'm OK with that question. But what do I want to say with the answer? Well, let's go ahead and do this. I could go to looks again. I could grab another say block, let it snap in. And I could say something like, hello, comma, David. But this is going to be the first of many bugs that I make, intentionally or otherwise. Let me click the green flag.
It's going to wait.
Scratch is now, just like in a web browser, prompting me for some input here. So let me go ahead and type in my name, David, enter, and voila, like it works. Hello, David. I'm kind of cheating, though, right? Because if I zoom out, stop, and play again, let me type in like Yulia's name here, David. Enter. And it still says hello, comma, David. So that didn't really implement the idea that I wanted. All right, so how can I fix this? Well, it seems that this time I want more than a side effect. I want to use the value that the human types in. And for this, we need another feature of functions, which is that not only can they sometimes have side effects, something visually happens, some functions can hand you back a value, a so-called return value that will allow you to actually reuse whatever the human typed in. So a return value is something that gets virtually handed back to you, and you can store it in something called a variable, like x, y, and z in mathematics, and you can generally reuse it one or more times. So let me actually draw our attention then to, at left, not only the blue puzzle piece, ask what's your name and wait, but notice that there's a special puzzle piece below it, this blue oval called answer, and that represents what a computer scientist would call a return value. So MIT has kind of bundled it together side by side to make clear that one of those pieces relates to the other. What it means is that I can do this. I can drag this oval and use this oval as the input to the say function. Now notice it's not the same size, but it is the right shape, so that's OK. Scratch will sort of grow or shrink things to fit properly. But this too isn't quite right. Let me go ahead and do this.
Is it the link that
Let me go ahead and stop that. Click the green flag. I'll type in my name again, DAVID, enter. And it's just kind of like weird or rude. Like I wanted a hello at least, and it just said David on the screen. OK, so I can fix that. Let me stop with the red stop sign. Let me just separate these temporarily, and I can leave it in the middle there, but they have no logical connection temporarily. Let me go back up to looks. Let me grab a say block, a second one, and let me go ahead and say, just to be grammatical, like hello, comma, space, and then I'll reconnect this here. So at the moment, it looks like what I want. I want a hello, comma, and then the return value printed out based on whatever the human typed in. So let me zoom out. Let me click the green flag. Again, what's your name? DAVID, and watch the cat's side effect. Enter. Still not greeting me properly. There's no hello. And if in case it was too fast, let's do it again. Green flag, DAVID, enter. It rudely just says my name, which is weird. What's the bug here, though? It's a little more subtle.
It's skipping over the hello say, which is the answer.
Yeah, it's just too quickly going over the say command or the say function in this case. My Mac, your PC, your phone, it's just so darn fast. Both are happening, but too fast for my human eyes to even notice. So we can solve this in a number of ways. I could actually use a different puzzle piece altogether. In fact, MIT kind of anticipated this. Notice the first puzzle piece in purple is say hello for a specific number of seconds. And you can specify not just the message, but the number of seconds, ergo 2 inputs, otherwise now known as arguments to a function. An input to a function is just an argument now. And that would be a fix here. I could maybe a little more explicitly do this. I could go under events, scroll down a little bit, and under control in orange, I could grab a wait block, and I could kind of insert it in the middle. And this might actually help. So I could click on the green
That's just
flag,
gonna print hello, and
DAVID,
then
enter,
we want them
hello,
to be
David,
sent
and I can
together.
change the timing to be a little more natural. But what if I want the cat to just say, hello, comma, David, all in one breath, so to speak? Well, for
Upstream, like
that,
you
I'm
would in
going to need to
Python.
use a slightly different technique as follows. Let me go ahead and get rid of the wait. Let me get rid of the second say block and stop the cat with the stop sign. Let me go under operators here, and let me somewhat cleverly grab this, a join block at the bottom. By default, it's using apple and banana as placeholders, but those are white ovals, so I can change those. Let me drag this over the white oval for the say function and let go, and it will snap to fill. Let me go ahead here and type hello, comma, space instead of apple.
And throw an answer there.
And what should I do instead of banana?
You need to put an answer to the question.
Yeah, so the answer return the return value. So let me go under
looks
sensing again.
sensing.
Let me just drag another copy of it, and you can use these again and again and again. They don't disappear. I want to drag answer over banana so that the second input to join is actually, if you will, the output of the ask block, like that, and it snaps to fit. So now, if I go ahead and click the green flag once more, DAVID, enter, now we have the sort of behavior aesthetically that I cared about. But beyond the aesthetics of this, the goal here really was to map it to, again, the same paradigm, which we'll see here. The algorithm and the output and the input for this example are as follows. The input to the say block was, quote unquote, what's your name? The function, of course, implementing that algorithm in code was the ask and wait block. The output, though, of the ask block, recall, is not some visual side effect. It is a return value called answer, like a variable, a special variable like x, y, and z in math. But in this one, we generally in programming describe variables with actual words, not just letters. But this output of the say block, I kind of want to make room for it to pass it into the say block as a second argument. So let's do this. Let's take one step back and propose that now for the join block that I just used, it takes two inputs, hello, comma, space, and answer. The function in question is indeed the join block. The output of this had better be hello, comma, David. What do I want to do with the output of the join block? Well, let me clear the screen. Let me move this over, because now the output of the join block is going to instantly become the input to the say block, so that the output now in this multi-step process is the side effect of hello, David. So the fact that I nested these blocks on top of one another was very much deliberate. If I zoom in here, notice that hello and answer are on top of join. Join is on top of the say block. And if you think back to like high school math, this is like when you had parentheses and you had to do the things inside parentheses before the things outside parentheses. It's the same idea, but I'm just visually stacking them instead. But outputs can become inputs depending on what the function there expects. All right, well, let's make the cat more cat-like and do this. Let me throw away all the say block and just let go there. And let me introduce at bottom left a nice feature of Scratch whereby there's also these extensions that tend to use the cloud, the internet, to give you even more functionality. And in fact, I'm going to click on this extension up here, text-to-speech.
We're importing some packages in the Scratch here.
I suddenly get a whole new category of blocks at the bottom, text-to-speech. They happen to be green. But what's nice here is that I can actually now have the cat say something audibly. So let me drag the speak block here instead of the say block. I don't want it just say hello. Let me stop that. So let me go back under operators. Let me grab another join block because I threw the other one away. Let me change apple to hello, comma, space again. Let me go to sensing. Let me drag answer to banana again. And now let me hit the green flag. And let me type in my name, DAVID. And in a moment, I'll hit enter and...
Hello, David.
All right, it's not exactly cat-like. It was synthesized, but it turns out under these text-to-speech blocks, there's some others. Set voice to alto, for instance, seems to be the default, but let's change this. So notice that some puzzle pieces don't just take white ovals, they might even have drop-downs. So whoever created that puzzle piece decided in advance what the available choices are for that input per the drop-down. So I'm going to change it to squeak, which sound, or actually kitten, sounds even more apt. Let me zoom out, click the green flag. Type my name, DAVID, enter.
Meow, meow.
That's interesting. So it doesn't seem to matter what I type. So how about David Malin?
Meow, meow, meow.
So it seems to meow proportional to how long the phrase is that I typed in. It can get a little creepy quickly. Like if I change kitten to giant, let me go ahead and hit play, DAVID, enter.
Hello, David.
So you can sort of, for very non-academic ways, like start to have fun with this, but just playing around with these various inputs and outputs. But let's actually make the cat do something more cat-like and indeed meow instead of saying any words at all. So let me throw all of that away. Let me go now under sound. Let me drag the play sound until done. And notice in the drop down here, by default, you just get the cat sound. You can record your own sounds. There's a whole library of dogs and birds and all sorts of sounds you can import into the program. I'll keep it simple with cat. And let me click the green flag. All right, so the cat meowed once. If I want the cat to meow again, I could do this. If I want the cat to meow a third time, I could again hit play. So this is kind of tedious. If to play this game, I have to keep clicking the button to keep the cat alive virtually in this way. So maybe I want this to happen again and again and again. Well, let me just do that. Let me sort of drag and drop, or I could right-click or control-click, and then a little menu would let me copy-paste or duplicate blocks. But I'll just keep dragging and dropping. Let's do this. Cat's kind of hungry, unhappy. So this like slow things down so it's adorable again. So let me go under control. Let me grab one of those wait 1 second, and I'll plop this here. Another one, let me plop it here. Click play again. Cuter, less hungry, sure. But this program is now, I dare say, correct if my goal is to get the cat to meow 3 times. But now, even if you've never programmed before, critique this program. It is not well designed, even though it is correct. In other words, it could be better. How, might you think?
You could loop rather than calling each function 3 times.
So using a loop. And why? Why are you encouraging me to use a loop even though it works as is? Yeah, so to summarize, it's just easier to use a loop because I could specify explicitly in one place how many times I want it to loop. And moreover, frankly, any time you are copying and pasting something in code or dragging the same thing again and again, odds are you're doing something foolish. Why? Because you're repeating yourself unnecessarily. And this is a bit extreme, but suppose I want to change this program later so that the cat pauses 2 seconds in between meows. Well, obviously, I can just go in here and do 2. But what if I forget? And suppose this program isn't like 5 or 6 puzzle pieces. Suppose it's 50 or 60 or 500 or 600. Eventually, I or a colleague I'm working with is going to screw up. They're going to change a value in one place, forget to change it in another. So why are you inviting the probability of making a mistake? Just simplify things so that you only have to change inputs in one place. So how can I do this? Let me zoom out. Let me throw most of this duplication away, leaving me with just the play and the wait function. Let me now, under control as well, grab one of these. I could, for instance, repeat as follows. Let me grab a repeat. I'm going to have to kind of move these in 2 parts. So I'm going to move this down. It's too small, but it will grow to fit the right shape. Then let me reattach it up here. Let me change the default 10 to a 3. And now I think I've done exactly what you were encouraging, which is simplify. And I click play now. Meow. And yeah, so still correct, but arguably better designed as a result. I can keep things simple and change things now in just one place, and it will continue to work. But this is getting a little tedious now, I claim. Like, why am I re-implementing the idea of meowing? Like, wouldn't MIT have been better to have just implemented a meow puzzle piece for us? Because the whole thing is themed around a cat. Why is there not a meow puzzle piece? Why do I need to go through all of this complexity to build that functionality? Well, what's nice about Scratch and what's nice about programming languages in general is you can generally invent your own puzzle pieces, your own functions, and then use and reuse them. So let me go ahead and do this. I'm going to go under My Blocks in pink down here. I'm going to go ahead and click Make a Block. And I'm going to be prompted with this interface here. And I'm going to call this block literally meow, because apparently MIT forgot to implement it for us. And I'm just going to go ahead and immediately click OK. And what you'll see now is 2 things. One, on the screen, I've been given this placeholder pink piece that says define meow as follows. So anything I attach to the bottom of that define block is going to define the meaning of meowing. And at top left, notice what I have under my blocks. I now have a pink puzzle piece called meow that is a new function that will do whatever that other block of code tells the cat to do. So what do I want to do here? Well, I'm going to keep it simple for now. I'm going to move the play sound meow until done and wait 2 seconds, though. Let's change it back to 1 second to move things along. And now let me drag the meow puzzle piece over to my loop such that now what's it going to do? It's going to meow 3 times. And just to be dramatic, out of sight, out of mind. Let me, for no technical reason, just drag this all the way to the bottom of the screen and then scroll back up just to make the point visually that now meowing exists. That is an implementation detail that we can abstract away, not caring how it exists, because I now know at a higher conceptual level, if I want to meow, I just use the meow puzzle piece. And I or someone else dealt with already how to implement meowing. So now let me go ahead and hit play. OK, so same exact code, but arguably better design because I've now given myself reusable code. So I don't have to copy paste those several blocks. I can just use meow again and again. But let's make one refinement. Let me actually scroll down to where I did, in fact, implement this. Let me control click or right click on it. And let me edit the pink block that I created a moment ago, because I want to practice what I've been preaching about inputs. So I don't want this function just to be called meow. I want this function to also take an input. And just for consistency with our use of n earlier, which in computer science generally means number, let me meow n times. And just so that this puzzle piece is even more programmer friendly, let me add just a textual label that has no technical significance other than to make this function sort of read left to right in a more English friendly way. Meow n times. Let me click OK. And now notice this thing at the bottom has changed such that it's not only called meow, there's explicit mention of n, which is a circle, which is exactly the variable shape that we saw earlier when it was called answer. This is not a return value, though.
So
this is what, again, we're going to call an argument, an input to a function. So let me do this. I'm going to move this back up to the top so I can see everything in one place. And I'm going to make one modification, because my goal now is to make a new and improved version of meowing that actually takes into account how many times I want the cat to meow. So instead of using a loop in my own program under when green flag clicked, I'm going to detach this temporarily. I'm going to move this away. I'm going to move this code over here. And I'm going to reattach it here. So focusing for the moment on just the left, meow is now defined as repeating 3 times the following 2 functions, play sound and wait. But that's not quite right. I want to get rid of the 3. So what can I do? Because I created this input to the meow function myself a moment ago, I can actually drag a copy of it, overwrite, that is, change the 3 to be generally an n. So now I have a function called meow that will meow any number of times. And what's nice now is my actual program that is governed by that green flag. I can type in 3, I can type in 10, I can type in 100, and it will just work. And henceforth, I can again dramatically sort of scroll this down so we don't know or care about it anymore. Now my program is a single line whereby this notion of meowing has been abstracted away by just defining my own function or custom block. Questions then about just this idea, this principle of creating your own functions to kind of hide implementation details. Once you've solved the problem, therefore, you don't want to have to think about that same problem ever again. And that's the beauty of programming, typically. Oh, all right, well, let's do this. Let's now make this a little more interactive in code. Let me go to this green flag. Let me scroll down and just throw all of this hard work away, that we have copies on the course's website of all of these programs step by step if you want to review them in slower detail. Let's do this. Under control, turns out there's other ways to loop. There's this forever block that will just do something forever.
Infinitely.
So in the forever block, there's some place for some other code. And I'm going to move to the control section here and grab one of these. If block, so one of these conditionals. Let's plug that in here, and now notice if, and then there's this sort of trapezoid-like placeholder that's gonna probably fit what? The if is a conditional, forever is a loop, say and so forth have been functions. What was the other key term we used?
Bools.
So a Boolean expression. We need to put one of those yes, no, or true, false questions here. So what are those? Well, I've been using Scratch for some years, so I know under sensing there's one of these shapes here, touching mouse pointer question mark. The question mark literally evokes the whole idea of a Boolean expression being yes, no. It's way too big to fit, but it is the right shape. So let me drag it, let go. It's going to grow to fill. And now let me go to sound. Let me grab that play sound meow until done and put it inside that conditional. Such that what kind of program have I just implemented here, arguably?
A loop.
What will this program do when I click the green flag? Well, nothing at the moment.
Because you have to touch the pointer to something.
But I'm not touching the cat, so if I move the mouse pointer to the cat,
Ah.
Again. Again. It's kind of like implementing the idea of petting a cat, if you will, because I'm forever just waiting and waiting and waiting. Is the mouse pointer touching that sprite, touching that cat? And only if so, go ahead and play that sound meow until done. But now we can make things a little more interesting. Let me stop this. And let me do something actually completely different. Let me throw all this hard work away.
Oh, wow.
Let me go under extensions. Let me go to video sensing, because lots of laptops, my own included, has a little webcam nowadays. Let me approve use of that there, and you can see me in the frame. And let me do this. Let me drag one of these when motion exceeds some measure. And through trial and error, I figured out that 50 tends to work well. Let me step out of frame here and program off to the side. And if I go to play sound meow until done, notice that this is an alternative to using when green flag clicked. This is a category of block that's constantly waiting for what we'll call an event. An event is just something that can happen on the screen. A click, a drag, a mouse movement, and so forth. So let me zoom out here. And now, if I can do this, here we go. No, too slow. Still too slow. Oh, wait, did I click play? Let's see. Try again. There we go. OK, 50 is a little too high, apparently. So let's make this a little gentler. 10. OK, well, there we go. There we go. OK, so we've implemented now more physically the idea of actually responding to a cat, to petting a cat. So, oh damn it. OK. OK, so this is a bug. Like now, this is MIT's fault. So it's not stopping in response to the red stop sign. So what do you do in doubt? Most extreme, you reboot. For now, I'm just going to close the window. OK, so now we've seen all of those primitives that we saw in that pseudocode, but incarnated in this graphical programming language. And again, without parentheses and semicolons and double quotes and all that punctuation that we will introduce before long. But for now, we have the mechanisms in place where we can do some really interesting things. And just listening to that song on loop was not the best way to program. But the goal here is to really use it as just an intellectual exercise as to how that was implemented. And we won't do the entire thing in detail, because I will say back in the day when I was younger, I didn't necessarily write the cleanest code. And in fact, if we see inside this and we poke around the bottom of the screen here, you can see all of my different sprites. And the code is kind of complex. Like things just kind of escalated quickly. But I did not set out and write all of these programs all at once for each sprite. I pretty much took baby steps, so to speak. And so for instance, let me open up just a few sample building blocks here that speak to this, that are written in advance. So here's version 0. Computer scientists typically start counting at 0. And let me show you this example here that only has 2 sprites on the screen. We have Oscar the trash can, and we have the piece of trash. And now notice, what does Oscar do? Well, let me go ahead and zoom in on this script, as it's called. The program is a script. When the green flag is clicked, Oscar switches his costume to Oscar 1. That's his default costume where the lid is closed. Then Oscar does this forever. If Oscar is touching the mouse pointer, change the costume to Oscar 2. Otherwise, change it back to Oscar 1. So that whole idea of animation where Oscar's popping in and out is just like a quick costume change based on a loop inside of which is a conditional waiting for the cursor, like Anna did, to get near the trash can. Meanwhile, if we look at the piece of trash here, notice that the trash is actually not doing anything in this first version because I didn't even implement falling first. So let me hit the green flag. Nothing is happening in this very first version, but notice if I click on the trash and drag, as soon as I'm touching Oscar, there comes that trash can lid. And it was just the result of making this one program respond to that input. All right, what did I do next? Well, next, after taking that single baby step, I added one other feature. Let's see inside this version 1. Again, Oscar is behaving the exact same way, but notice this time, the trash is designed to do the following. First, I'm telling the program that the drag mode is draggable. That is, I want the trash to be movable when the user clicks on it. Then I tell the piece of trash to go to a random X location. X is the horizontal, so it's going somewhere between 0 and 240, but all the way at the top of the screen, 180. Then forever, the piece of trash just changes by -1. So it just moves down and down and down. And without looking at the second script yet, let me just hit play and notice, without even doing anything, And eventually, once there was lots of trash falling, like Anna was struggling to keep up with this, it's just moving one pixel at a time forever until, thankfully, MIT does stop things automatically if they hit the bottom, lest a 6-year-old get upset that all of a sudden their sprite is gone forever. So there is some special casing there. But what else is this trash doing? Let me zoom in here. The piece of trash, also when the green flag is clicked, is forever asking this question. If you are touching Oscar, then pick a new random location between 0 and 240 at positive 180 and go back to the top. So in other words, as soon as this piece of trash is dragged over to Oscar like this and I let go, it recreates itself at the top. It's just sort of teleporting to the top, and thus was born this feature. And I won't slog through all of the individual features here, but if we do just one more and see inside this one. So now, let me go ahead and hit play. Notice at the top left of the screen, there's a score, currently 0. But now when I click the trash and let go, notice that the score is being incremented by 1. And this, in fact, is how Anna's your score kept going higher and higher and higher. Every time I noticed, oh, the trash is touching Oscar, let's not only teleport, let's also increment a variable. And we didn't see this before, but if I go to this Oscar scratch now, you'll see that it is exactly the same. But if I now go to the trash piece here, and we go to when green flag clicked, you'll see that I'm initializing a variable in orange called score to 0. But if we scroll down to the bottom, Oscar is also doing another thing in parallel at the same time. When the green flag is clicked, Oscar is forever checking, is the piece of trash touching Oscar? If so, change the score by 1, and then go to top, which is another location on that screen. So in other words, even though at a glance something like Oscar time might look very complicated, and it did take me hours, the goal, especially with problem set 0, is not going to be to bite off all of that at once, but to take proverbial baby steps. Implement one tiny feature so that you feel like you're making progress, add another feature, another, and invariably you might run out of time and not get to the best version of your vision, but hopefully it'll be good, hopefully it'll be better, but you'll have these sort of mental milestones, hoping that you at least get to that point, because as you will soon discover, everything in the world of programming, unfortunately, takes longer than you might expect. That was true for me 25 years ago, and is still true today. Well, let me introduce one final set of examples here, this one written by one of your own predecessors, a former student. Let me go ahead and open up 3 baby steps, if you will, toward an end of implementing a game called Ivy's Hardest Game, whereby it's now more interactive, quite like Oscar time. So at top right here, notice, and I'll zoom in, we have this world that's initially very simple. 2 black lines, 2 walls, if you will, and a Harvard sprite in the middle. But when you click the green flag, notice that nothing happens initially, except that the sprite jumps to the middle. But I can hit the up key, or the down key, or the left key, or the right key. But if I try to go too far, even though it's not the edge of the world, it's only touching that there black line, it's still going to stop as well. So intuitively, how could you implement that type of program? How could you get a sprite, from what we've seen, to respond to up, down, left, right, but actually move when I touch my arrow keys? Like, what does it mean to move? Yeah. Exactly. So much like with representing information, at the end of the day, all we've got is zeros and ones. When it comes to algorithms, at the moment, all we have are functions and loops and conditionals and Boolean expressions, and soon some more things too. But there's not all that much we have at our disposal. So let me zoom out from this, and let me actually show you what the Harvard sprite is doing. It's doing this. When I go up to the green flag here, the Harvard sprite is going to 0, 0, so dead center in the middle, and then it's forever doing 2 things, listening for the keyboard and feeling for walls, left and right. Now, those are not puzzle pieces that come with Scratch. I created my own custom blocks, my own functions, to implement those ideas. Let's not abstract away for now. Let's actually look at these features, and indeed, to your instincts at left here, what does it mean to listen for the keyboard? Well, if the up arrow key is pressed, change Y by 1, move up. If the down arrow key is pressed, change Y by -1. If the right arrow key is pressed, change X by 1. If the left arrow key is pressed, change X by -1. So take sort of all the magic out of moving up, down, left, right by just quantizing it as plus, minus, this, and that. It's all numbers, indeed, at the end of the day. But what else is it doing? Notice that it did indeed bounce off the wall. So my other custom function, which I chose feel for walls to kind of evoke this idea, it's asking 2 questions. If you're touching the left wall, then change X by 1, so bounce in the other direction. Else, if you're touching the right wall, bounce in the -1 direction. And so what are left wall and right wall? I mean, I kind of cheated. I just used 2 more sprites. These sprites are literally nothing except black lines. But because they exist, I can ask that question in my conditional saying, are you touching those other sprites? And I could have colored them any way I want. But this is enough if I zoom in to implement this idea of going up, down, left, and right, and preventing the sprite from leaving that little world. All right, so if you'll agree that there's a way now to implement motion, up, down, left, right, let's go ahead and implement this idea by adding a rival into the mix, like a Yale sprite. And what the Yale sprite is going to do, if I click the green flag, is this. So Harvard at the moment is still going to be movable with the arrow keys, up, down, left, right. But Yale, for better or for worse, is just going to mindlessly bounce back and forth from left to right forever, it would seem. The operative word being forever. So how's that working? Well, let's look. Here's the Yale sprite at the bottom. Let's zoom in on its actual code here. The Yale sprite starts at 0, 0. It points in direction 90 degrees, which means left, right, essentially. And then it forever does this. If touching the left wall or touching the right wall, turn around 180 degrees. So I don't want the Yale sprite to just stop by moving it 1 pixel to bounce off slightly. I want it to wrap around and just keep going and going and going forever. And that's it. Everything else is the same. So one final flourish. Let's add a more formidable adversary like MIT here, whereby if I zoom in and hit play, notice that if I move the Harvard sprite, MIT comes chasing me now. Now, how is this actually working? Yale is just kind of doing its thing, bouncing back and forth. Now MIT is really latched on to me. And it's following me up, down, left, right. So how is that logic now working? Well, again, it's probably doing something forever, because that's why it's continually doing it. Let's click on MIT. This, too, is pretty simple, even though it's a pretty fancy idea. Initially, the MIT sprite goes to a random position, but thereafter, it forever points toward the Harvard logo outline, which is just the long name that your predecessor or former student gave the name for that sprite. And then it moves 1 step, 1 step, 1 step. So suppose this were an actual game, and in games, like, things get harder and harder, the adversary moves faster and faster. How could we make MIT even faster by changing just one thing here? How do we level up? Change the 1 to like 2 pixels at a time, 2 steps at a time. So let's see that. Let's go ahead and zoom out. Let's hit play. And now notice that MIT is coming in much faster this time. All right, so it wasn't noticeably faster. Let's do this. Let's move 10 steps at a time. So 10 steps faster than originally. I mean, now notice it's kind of twitching back and forth in this way. Why? Well, probably, if we worked out the math, probably the MIT sprite is touching the sprite and it's bouncing off of it. But then it's realizing, oh, I went too far. Let me move back. Wait a minute, I'm still touching it. Let me move down. So you can get into these perverse situations where there is actually a bug, be it logical or aesthetical. But in this case, we probably want to fix that. So 10 is probably too fast for this to work particularly well.
Okay. Awesome, you guys. Well, that was week 0, lecture 0 on Scratch, CS50x of the 2025 version. Awesome.